then widely adopted by the Romans. So how many prisoners taken at random have died by having their hands and feet pierced? Obviously a lot of people. Millions were crucified by the Romans. But if I said less than 1 in 10,000, am I being generous? I think so. Okay, so what I've done here, we've concatenated a list of prophecies. Born in Bethlehem, king on a donkey, 30 pieces of silver, temple potter, and all that business. Wounds in the hands, no defense, though innocent. Died with the wicked, grave with the rich, and crucified. Now the question is, okay, if those are the probabilities of each one of these individually, what's the probability of a particular person having fulfilled all 8 of them? Well, that's a dilemma, because now we're dealing with composite probabilities. And for the purpose of this discussion, we'll assume that these things are randomly distributed. Let's talk about, let me give you a little tutorial on composite probabilities. Let's imagine in this audience that we have 60% of you are men and 40% are women. And suppose we blindfolded someone and had him pick one of you at random under some conditions that would make it equally likely to be any of you. What would be the chance, if he reached out and touched one of you, that it was a female? Well, how would you analyze? Well, if 60% are male and 40% female, he's got a probability of 40%, or probability of 0.4, that he encountered a female. You with me so far? Okay. Let me give you a different example. Let's assume that 60% of you are right-handed and 40% are left-handed. Let's assume for this discussion that those are randomly distributed, independent of sex. They're just, we got right and left-handed people in a 60-40 ratio. What's the probability that someone selected randomly would be left-handed? Again, it would be 40%. You're with me so far? Here's the point I'm trying to make. What's the probability, assuming these attributes were randomly distributed, of somebody getting a left-handed female? Well, what you do is you take the one distribution and you take the other distribution, and you would combine those two distributions, and the ones that met both conditions would be the product of those two probabilities. In other words, 0.4 times 0.4, 0.16. In other words, if 40% of you are female and 40% are left-handed, the combination would be, 16% of you would be a good estimate of the probability of being a left-handed female. Are you with me? In other words, what I'm trying to get across, a simple way of getting an estimate here is simply take the product of the probabilities. Okay, having said all that, probably a 0.16, let's take a look at these 8 prophecies. I've made them in powers of 10, so multiplying them just becomes a question of adding up the zeros. See, 1,000 is 10 to the third, and 100 is 10 to the second, so 100,000 is 10 to the fifth. 2 plus 3, you with me? So all I need to do is add up the zeros. The probability of one person fitting all these things would be 1 chance in 10 to the 28th, but I need to work out the total people that live. So I take the 100 billion, I'm going to assume 100 billion population as a guess. So if I take the combined probability of 10 to the 28th divided by 10 to the 11th, I now have still a very large number, a number by 10 to the 17th. Now, if we were in a statistics class in graduate school or whatever, and I was going to try to get across to you what I mean by 1 chance in 100, what do I mean by that? Well, the way I demonstrate that is I might get a bucket. I would put in that bucket 100 silver dollars. I'd take one of them and mark it with some lipstick or nail polish or something, and I'd mix them all up. And the chance of my reaching in there and picking one at random is 1 chance in 100 of getting the one I marked. You with me? That's a way of demonstrating what I mean by that stochastic. That's a stochastic statement. Most people are not familiar with dealing with that. So that's okay. So what I want now, what I need to do to demonstrate this probability that we're talking about here is I need a bucket that will hold 10 to the 17th silver dollars. That turns out to be a pretty big bucket. That's a lot of silver dollars. In fact, if I want a bucket of 10 to the 17th silver dollars, I need to take the state of Texas, and fill it with silver dollars, and it'll end up being about 2 feet deep. That's 10 to the 17th silver dollars. And so what I would do then is pick one of you, blindfold you, and put you into a situation where you have an equal likelihood of being exposed to any particular. I mix them up in such a way and route you in such a way that you have an equal chance of getting any one of those silver dollars. When you're going to reach down there with your blindfold and pick one, the chance that you got the one we marked is 1 chance in 10 to the 17th. Does that get it across? So you with me so far? You recognize that? It's a way of demonstrating just how unlikely that is. But we're not through. I said we had 300 prophecies to deal with. We took 8 of them. Let's assume I take another 8, so I have 16 altogether. To spare you the time, we're not going to actually pick up another 8, but if we did, the 8 that I would add would be more technical, more precise, less likely. I'm going to assume, for this simple analysis, that the next 8 are no less likely than the ones I've already picked. That's a very generous assumption, obviously. So I've got 300 to choose from. The next 8 would be more specific, that is less likely than the previous ones. But I'm going to assume no decrease in likelihoods. I'm just going to add 8 of an equivalent kind. So now I have 10 to the 28th times 10 to the 28th. We add the exponents, so that's 1 chance in 10 to the 56th. But again, I subtract out my 10 to the 11th population over that time. So now I have a 10 to the 45th, okay? So now I need a bucket of silver dollars that'll hold 10 to the 45th silver dollars. That's a lot of silver dollars. Let me give you a feeling for how many that is. How big a bucket do I need? I need to make a ball of silver dollars that is 30 times the radius of the earth to the sun. Can you imagine that? You can't imagine that many. And 30 times the distance of the earth to the sun. A ball of silver dollars. Now in this case, we'll get our volunteer that's going to pick, and we've marked one of these and mixed them all up. I get one of you blindfolded and in a spacesuit and send them out there under conditions that would make it equally likely to be exposed to any of them. And you reach in, and if you pick the one that we marked, that's 1 chance in 10 to the 45th. So I'm going to do this one more time, because I say this is getting a little ridiculous, Chuck. This time, instead of doubling, I'll just triple. I'll go from 16, I'll go to 48. Bear in mind, I got 300 to choose from, but I'm going to reach a little further. And I'm going to, again, assume there's no decrease in likelihoods. Actually, I can find prophecies there that are so rare they stand on their own in terms of this kind of analysis. But let's just assume that the rest of them, to make up 48, are no less likely than the first 8 we picked. Well, that's 10 to the 28th multiplied by itself 6 times, 10 to the 168. And now I have to subtract my 10 to the 11th out of there, so that's 10 to the 157th. That's a pretty big number. How big is it? Well, the first problem I've got is silver dollars won't work. They're way too big. I need something small. I need the smallest thing you can imagine. What is the smallest thing you can imagine? An atom. Huh? How's that? It may surprise you to learn that there are estimates of the number of atoms in our galaxy. I want to make a ball of every atom in our galaxy. It turns out there's a commonly accepted estimate among scientists about 10 to the 66th atoms in our galaxy. Well, that means if I make a ball of every atom, if I'm going to consider them as my sample, I'm way short of what I need. I need 10 to the 157th. Okay, so I'll make such a ball for each atom in the universe. So now I got 10 to the 66th times 10 to the 66th. Well, that's 10 to the 132nd. I'm still far short of 10 to the 157th. Okay, I've got a ball for every atom in the universe consisting of as many atoms as there are in the universe. I'm going to imagine that crazy exercise happening every second since the universe began. Well, that's about 10 to the 17th seconds if you do the math. And now I'm still only 10 to the 149th. I've made a ball of atoms equal to all the atoms in the universe. I'm going to do that for each atom in the universe, and I'm going to do that whole silly thing every second for 16 billion years. Is that a big number? I am still short of my 157th. In fact, I'm short by over 100 million to 1. You say, okay, this is pretty silly. What's your point? Here's my point. I am more convinced that Jesus Christ was the Messiah of Israel. I'm more convinced of that than I am of any other fact in my command. I'm more convinced of his identity than I am my own. Now, I have no reason to doubt my identity. I've got a birth certificate. I know my parentage, etc. There's no little gimmick here. And yet, I also realize I could not attach this kind of certainty to any other fact I know of. And and incidentally, we've only dealt with 48 of 300. So you can get some idea why some of those estimates aren't that critical. You follow me? If I could make them even looser, you're still, you're out in beyond the realm of reasonable doubt. Beyond the realm of reasonable doubt. And incidentally, in going through this little exercise, I've missed the most amazing ones.